All right. Okay. So we are nearing the end of the semester. In fact, sort of the final stretch. So there's a bunch of remaining things. There's the homework, which is due now. There is the last programming project, and there's your final presentation. That's it.
What are our final presentations?
The final presentations are either, depending, we need to work out the schedule, and they are the final day and the last day of class, which is April 25th, I think. So there's April 25th and April 27th. So that last week is allocated to final presentations. I think that's enough time for everyone to give a 15-minute talk with about 5 minutes of questions.
Isn't the last day of class April 22nd? No, I'm wrong. Never mind.
It was 23rd, I think is the last day. 22nd is a Sunday, isn't it?
I don't think so.
No, I think it's the 20th.
No, I think it's 25th. Okay. Anyhow, read the syllabus. I wrote it for a reason.
There's a Monday
Sure.
class before.
What's that?
There's the Monday and then final start.
Yeah, and so that's the Monday, and then our final is Wednesday.
Okay.
So it would be the 25th and the 27th.
That's right.
Who's
Yeah,
the
as I said.
schedule for that yet?
What's that?
Like who's presenting when?
Yep, and basically what I'm doing is I now have everyone's listing of who's got what. And so I'll send that out probably tomorrow, so you can work towards that. And yeah, we'll go from there. Alrighty. Yeah. Other questions before we get started? Okay, right. So actually, let me collect the homework before I forget. So we have homeworks, and I'll take those now.
Alright.
Here's what it is.
I hand
Here's what it is.
because
No,
it's
that's
easier.
my other one.
Doing all the columns.
All right, great. Thank you. Any more? Are you stable? Wow, that's a heck of a stapler. That's one heck of a stapler.
LSE and they're just
Yes.
non-functional.
Yeah.
It's incredible.
All right.
Yeah.
So today, we're going to talk a little bit about
English quality.
zigzag persistence. Which is a family of ideas traceable to same Carlson as before, and Silva. 2008 by a paper of the same name. So very, very recent. In fact, sufficiently recent that when I asked some of my colleagues who do persistent homology as their primary form of research, if there was anyone who has written up zigzag persistent homology as a library. I was hoping there'd be a whole ecosystem of these things. As far as I know, there's exactly one library out there that does it, and that's, so the only library that I know of is by Dmitry Morozov. Oops.
Is there like a central repository for these? Like CRAN for R?
Not really.
So how do you find that?
On his website. You search for him in Zigzag Persistent Homology. You'll find it. The library is called Mayer-Vietoris. And so basically this is very much cutting edge. To the point of being, well, gosh, that's pretty neat. It would be nice if someone wrote it up. Anyhow, the concept, however, is rather useful because if you work with the persistent homology as defined previously, there's a little bit of a problem. And that little bit of a problem is that not all of your data want really good filtrations. So the issue is that not all interesting data sets above as filtrations. That's the issue that Zigzag's persistent homology tries to solve. Now, I've been actually couching this course from the beginning, leading towards being able to write down Zigzag persistent homology in a reasonable fashion. Yeah.
This is the issue with normal persistent.
This is the issue with normal persistent homology. This is Zigzag persistence solves this.
That's because of like, oh wait. That's because of restrictions on computing the Vietoris rips?
No, it's actually, so if you start with Vietoris rips, then you're in good shape to think of it as a filtration. But you don't necessarily want to start with Vietoris rips.
Would it be a filtration on epsilon?
It is a filtration on epsilon. The problem, however, is that Vietoris rips complexes get super big, super quick. And so what do you do when things are too expensive to take the entire population? You sample. If you're a statistician, you sample, and that's the right thing to do. Now, the problem, of course, is if you start doing a whole bunch of samples, they are not related to one another in a filtration. So, if you can construct a Vietoris-Rips complex using all of your data, great. That's a filtration. But if you can't, and are forced to sample, then you no longer have a filtration. Because those different samples are not related to one another in a nice way. Make a very severe example. Let me make two samples, a black sample and a blue sample. If I look at the Vietoris-Rips complex associated to the black, a single epsilon of the black complex, it'll be kind of all over here. So as I make epsilon a little bigger, maybe I'll get that particular guy, that particular simplex. And if I do it over the same kind of thing over here with the blue one, it has nothing to do with the black one at all. Not a filtration. The blue ones are not a subset of the black ones, vice versa.
Why would the data points be separated?
Oh, this is a really extreme case where I've grabbed two samples in a rather unlucky way.
How do you choose, so, okay, when you're constructing Vietoris-Rips complexi?
Complexes, yes. Complexes.
By,
Yes.
so are you throwing like a dot randomly, or dots randomly, and then constructing epsilon balls around them, and that's how you construct your samples?
So the data points are given to you. There are some high-dimensional data.
Yeah.
So now when you construct your sample, you're picking, say, random points from that
Right.
collection.
That's what I'm asking.
Yes.
So you have a bunch of points that are given, that's your data. So to sample, you just throw a dart there, and then make an epsilon ball around said dart?
Right.
Okay.
So, I mean, really what you could have, I mean, this is probably a much more accurate representation of what's going on, is you have unsampled points in red, as in points you've just ignored. You've got sample number 1 in black, and sample number 2 in blue. And you're trying to make some kind of inference about your whole population from either this sample or this sample. I mean, that's what you do in statistics. And the idea is that if the black or the blue sample is big enough, then I should be able to draw some conclusions about everything, including the points I didn't bother sampling. But as this example indicates, I mean, this is kind of a law of small numbers kind of issue, which is, well, I'm just unlucky. But you can imagine that these samples may have nothing to do with one another, and at the very least, they're not going to be filtration. Yes?
So the issue at hand is that they appear to be two different connected components,
Yeah.
but in fact they're not because data points exist between them.
Amongst them, yes.
If we happen to pick one of those red dots in between,
Sure.
then they would be.
Well, but think of it this way. The problem is that these, not just that they're different in some sense, but they don't fit together. The black samples and the blue samples don't together form. If I look at the blue filtration, that's not a filtration of the black points. And vice versa. The black points, if I look at that filtration, has nothing to do with the blue points. In fact, any of the simplices that show up with the black points probably don't have anything to do with the blue points, unless I happen to really, very luckily, picked some points in the overlap. So, I might, in the final analysis, let me say I enlarge my black sample, so I happen to pick that one also as a black point. So maybe I get this edge here. But I don't necessarily get these other edges, and they don't necessarily fit together. One is not a subcomplex of the other, under any reasonable circumstances. So the point being that my samples being different, unlike in the usual statistical case where I can do something together, that's sort of a problem. So what zigzag persistence is supposed to do is it's supposed to solve this problem by looking back at what statistics tells us about what you should do if you have two, not necessarily disjoint, but somehow overlapping samples, and I want to put them together.
Subtraction intersection.
That's exactly the right idea. We want to build an algebraic machine that does something like that. We want to build an algebraic machine tailored to homology and persistent homology that does the inclusion-exclusion principle. That's what we want. Because the inclusion-exclusion principle is how you sew together different distributions. In fact, if you take the stat hat off, put the math hat on, and ask the same question, what kind of mathematical object do you use inclusion-exclusion principle for?
Sets.
Sets, and what else? A little more sophisticated than sets, but distribution type things. Anyone?
It's not a category. Right?
No. Not topology, not a category. Something very basic, something that you use in calculus.
Function.
Huh?
Function.
What about the functions? What do you do to functions in calculus?
Differentiate.
And
Integrate.
integrate them. It's an integral. And integration involves inclusion-exclusion principles. Think about it this way.
Oh. Interesting.
And so what we really want to do is we want to build a sort of an algebraic machine that does things like integrals. So here's the idea. So this is the intuition. Distributions can be merged because they're integrals.
You mean here probability distribution?
Yeah.
Okay.
So if I have two sets, let's say I have a set A and a set B. Two sets in R. And I have a probability distribution. Well, if I have a probability distribution function on R, what's that? Well, it's a thing that looks a bit like a function. Looks like an F.
Integral has to sum to 1.
Right. Integral of f dx on R is 1.
Assuming it's a continuous distribution.
Yeah, sure. I've been playing a little fast and loose because I said intuition. I don't want to get too wrapped around the X. We could do it that way, but it involves a little more machinery. Okay, so what's one of the very important things about integrals is the integral over the union of a set is the integral over each part of the set minus, well, I've double counted, so I need to get rid of the intersection. This inclusion-exclusion principle. It's not that A or B have anything to do with one another. The sets A and B that I've written here, I mean, really the only thing that I need to do is be able to have them be sufficiently nice that I can write the integrals over them. To study measure theory, I need measurable sets, and I need F to be a measure, really. But they don't really have to do anything with each other at all, but I can find the measure of their union, or the probability that my event happened in the union of them, provided I know the intersections. So I can leverage the intersection. Now this seems like a very basic concept, but now I want the same kind of algebraic thing to happen on the level of topology as well. Now it turns out that concept actually does work here, and that really is what drives the right answer, and this is what drives what zigzag persistent homology is about. So here's how you make that work. So the observation is, now, let's go back to our chain complexes. So let's draw a line in the sand and suppose we have two subcomplexes, A and B, that are a subcomplex of a simplicial complex, X. Now, it may be that the subcomplex A and the subcomplex B have nothing to do with one another. Completely unrelated. But, assuming they're nice enough, we should be able to talk about them, and since they're abstract simplicial complexes, perhaps, then that's sufficient. Okay, so here's the idea. The idea is the following observation. And both of these things here, they also are subcomplexes. Why? In fact, you can call this a lemma. Yeah, why?
Because they're subsets of X.
Well, what does it mean to be subcomplex? It means that I can look, if I grab a hold of one of the faces in here, I've got all the lower dimensional faces attached to that. That's what it means to be a subcomplex. So,
A union B is pretty obviously.
what's that?
A union B is pretty obviously.
Yeah, because I just made it bigger. I haven't added any trouble at all. Now what about the intersection? I could have possibly thrown something out, right?
Yeah.
Yeah, but if I throw something out,
If there's an element in A intersect B, if there's a face in A intersect B, then it is an A and B, which means that all its other elements must also be in A intersect B. Or all the smaller.
all those lower dimensional faces have to be in there as well. All right, so these guys are also subcomplexes. The moment I've written this down as saying these are two subcomplexes, everything else comes along for the ride. It's kind of like a measurability criteria over here, which says that these sets are nice enough that I can intersect them. Over here it's the sigma algebra property. Here it's basically the same deal. In fact, it's saying the set of subcomplexes forms a sigma algebra. That's sort of a measure theoretic way to look at the situation. Okay, now there's something else going on here, is that these aren't completely unrelated to my A and B to start with. In fact, if I sort of order them by size, this guy here, the intersection, is somehow smaller than B. There's a function that just allows me to reinterpret every element of A intersect B as an element of A, and reinterpret every element of A intersect B as an element of B. Of course, the same idea works going this way. So these are all inclusions. Which is to say that I'm just reinterpreting the elements as being elements of a bigger set. This diagram commutes. Because why? Why does the diagram commute? Well, start here. Pick an element in the intersection here.
Then you're obviously in A,
You're obviously in A.
which means you're in A or B.
And yeah, of course, so you're in A or B. But that same point is also in B, isn't it now? And it's like the same point over here. So it's, yeah, diagram commutes. Sort of pretty trivial. Okay, but this bit of information now allows us to take a look at the chain complexes associated to A and B. A and B are simplicial complexes in their own right, so they've got chain complexes associated with them. So we can look at the chain complexes associated to these four spaces and see how they fit together. Okay. So let's consider chain complexes. There's for A. Oops, this is B. And for the last one. Okay, so there are four chain complexes, one for each of these various spaces. Now, I know that A is a subset of A union B, and so is B. What does that mean? Well, it means if I take a look at the K simplices of A or B, they're also in A union B. What does that mean I can do at the level of chain complexes? Well, I can just translate those K simplices, the vectors associated with them, to vectors associated with the K simplices over here. Take each simplex here, say, grab a simplex. It corresponds to a vector in this vector space. That's a whole bunch of zeros, 1, 1, and then a whole bunch more zeros. That same simplex shows up down here, so I can build up a linear map. Of course, I can do that for the K-1 simplices, and the K-2 simplices. And don't you know the whole thing commutes? Why? Yeah?
Because that guy.
Because that guy commutes, basically. Because really not a whole heck of a lot is going on. Well, all right. What works for B also works for A. Now, gosh, I ought to be able to do the same thing with these intersections. See, everything in here shows up either in here or in here. And of course over in here.
So it just goes straight up.
So these guys can zip straight up. There you go. All right. Now, this is unfortunate because we really only have a two-dimensional board and I really want a three-dimensional one. But what I've done, really, now the category theory, what I've done, really, is for everything, I've really just, that big diagram can be kind of summarized like so. Just look at chain complexes. Now, instead of being inclusions, these are no longer inclusions, these are chain maps, like so. Basically, in black is involving the simplices, and now in blue involves these various vectors associated with the simplices grouped up in different dimensions. And the other point by saying they're chain maps means that they commute with the boundaries. But that's pretty straightforward because I'm just dragging along the boundaries along for the ride anyway. Well, that's kind of awful handy. So what this is saying, if I have chain maps, what does that mean about homology then? The homologies are kind of related too, aren't they? Now, these were injective maps because each simplex here maps to exactly one simplex over here. And each simplex here maps to exactly one simplex there. So those are injective chain maps. It's probably not the case they'll be injective on homology. That's certainly the case. But the point is you end up with a diagram that looks a bit like, well, looks basically like that, except now everything's got H's in front. So, applying homology, I get something that looks like this. And then these are various linear maps. And again, the heavy dot saying that it could be any of various K's. These are just now plain old linear maps with essentially no restrictions on them. So what this says is this says that the homology of the union does actually have something to do with the homologies of these smaller guys, provided you know something about the intersection. What says that? It actually says a lot more than this if you push it the right way, which is not apparent in this diagram. So there's a bunch of different directions we can take this. The first thing I want to do is I want to show how this straight up helps you solve the problem of not having filtrations. Then I want to delve into some of the more refined aspects of this to show you how this plays out looking like integration. Okay. So let's suppose now that we have many related samples. How do I do? Now, what do I mean by related? Well,
IID.
no, not really. I mean something a little different. I mean that I have consecutive overlapping sets of samples. So I have something like this. So our data is a point cloud. Here's a point cloud. And the second thing we're going to do is we're going to take a bunch of different samples. Our case of I, subcomplexes. Vietoris Roots complex. With some and the next thing that I'm going to assume is now the relatedness.
The intersections are not.
That's right, that the intersection of consecutive, those are not empty, and that if I take the union of them all, I get the whole Vietoris Roots complex.
So the samples are covering.
The samples are covering. That's right. And the one to the next, to the next, to the next fills out everything. Okay? Well, so what I'm going to do is something like this. Okay. I'm going to write a big diagram. And the diagram goes something like this. Actually, I'm going to start it out with lower stress. Okay.
Is this going to be like a new page kind of big diagram?
I'm just going to fill up.
Good question. Sorry, I didn't answer your question, I suppose.
But why stop here?
But wait, there's more.
That's right. Oops. And you gotta like keep going. And here's the interesting thing. The interesting thing about this is that this is a whole bunch of those little diamond diagrams that I had on the previous board. A whole bunch of them that sort of fit together. It's kind of laid out in a nice grid format. The other interesting thing about this is assuming these were like came from points in some reasonable fashion, these are subcomplexes in some reasonable fashion, I can tell you pretty much what's going on in the intersection between these two guys. What's in the intersection between these guys? Oh, this. Oh, like what's in the intersection between those? Oh, this. Oh, really? So there's some kind of iterative procedure that I can do to sew together my data. That this is sort of the finest level, and I can build up in level this way. So I've recovered the notion of my filtration. Now, not necessarily that I want to compute everything like up here, right? That's probably bad. And the whole point of doing this was because I couldn't address the entire population. Way at the top of the board, way well beyond the top of the board, is the whole thing.
At least it terminates.
Yeah, at least it terminates because I've run out of points. Way up at the top of the board. I don't want to compute that, I want to work down here. Down here, things are smaller. These are smaller numbers of points. So I really don't want to have to progress too far up the board. So ideally, what I want to work with is I want to work with just this part. I don't want to have to progress up higher. Now, if I'm going to do that, I really need to be able to kind of extend my diagram this way. Of course, I could keep going that way. But again, that too terminates. Why does that terminate?
Because you only have so many points.
Yeah, because eventually I run out of points and I'll have a whole bunch of empty sets down below.
Yeah.
This actually is a nice property of sets. It's called well-foundedness of set theory.
How does that mean?
It means that I don't run into serious disasters if I do this sort of thing, starting with small sets. Yeah.
So ideally, are we just working with the AIs and the union of?
Unions and the intersections. Really, this is all I want to work with. And important theorem now is that anything that I would like to know about up there, way at the top of the board, can be figured out from this information here. So I'd never actually have to address the whole situation at the top, computing with all the big collections of points. Because remember, if this has got n points, this has got m points, this has got at most n plus m points, maybe minus the overlap, but certainly an upper bound is n plus m points. So the point is I don't want to work with that big collection of points. I want to kind of limit my attention to smaller collections. And I'm able to do that. And how does this work? Well, the way this works is because I'm actually able to write down the homology of the union based on the homologies of these guys, each of the different component pieces, and the intersection. Now that diamond that I wrote down on the previous board doesn't finish the story. We need something a little more algebraic to make that actually work, and something a little more refined to make that work. So I want to delve into that. But the main idea of zigzag persistent homology is that this structure here, in black, circled in green, well, it's no longer a straight filtration, it is zigzaggy. That is the zigzag, and zigzag persistent homology is about doing persistent homology in this context here. Now here's the cool thing about this, and I've structured the course with this in mind, so that if you hit each of these guys with the homology functor, asking for homology each of these superficial complexes and their relations, what do you end up with? You end up with a quiver representation, still. Vector space, linear map, vector space, linear map, vector space, linear map, whole bunch of linear maps. They don't all go in the same direction anymore. They go in any direction you like, but you can still compute a barcode diagram for them. It's sort of a pain in the neck, because where do you start the bars? Well, you start the bars here, and you check for linear dependence up here. It's sort of nasty. And if you look at this, you might say, well, gosh, I didn't really have to do this in any particular orientation with the arrows, and in fact, theorem proven by Carlson and De Silva, is that you really can do it any way you like, and there's a nice algorithm for that. Now, it sort of becomes somewhat of a mess. But nevertheless, it can be done. So if you just have the vector spaces and linear maps, you can make this whole thing work. But it's important to realize how these things fit together. And that's what I want to zoom in on now and pull out this inclusion-exclusion principle from the sort of diamond. It goes under the name of the diamond principle. Kind of obvious. It also makes use of something called the Mayer-Vietoris exact sequence. Which I'll write that down and delve into that, show you how that works, and show you how that answers this well-posedness, that everything that I need to know down here describes everything I'd like to know as I go up in size.
Who is Vietoris?
Vietoris is a reasonably famous algebraic topologist. Yeah.
So when you wrote down the diamond homology spaces with the big dots,
Yep.
is that saying that actually the relationship between the homology spaces is still such that we just take unions to get the,
No.
like the homology?
No, and actually, that's what I'm gonna delve into in a lot more detail now.
Okay.
I'm gonna show you how that works. Yeah,
I thought for a second that when it went from A to a
Yeah.
union, that it would be an induced map, but,
it is an inducement.
oh,
You're right, absolutely.
okay.
Yeah, so, all right, let's sort of summarize the state of play. We've got A, B, A union B, A intersect B. These are spaces, or let's say these are simplicial complexes. With inclusions. We turn that into chain complexes. With chain maps between them, and even better, these are injective chain maps. In particular, simplicial complexes got turned into chain complexes, the inclusions translated directly into injective chain maps. And then the final transformation homology spaces, but just plain old linear maps.
And the method for going between, say, things in the first
Yep.
row there are functors?
Yes, each of these are functors. Each of these are functors that translate this particular category into the next one.
What are the names of those?
So, this one here is the homology functor. And this one here, I don't know, that chain complexization functor doesn't really have a standard name. Now, nevertheless, this is not hard to write down. In fact, this guy here is something that in your third programming project you'll be implementing. In your first programming project, you implemented this one. You've already done this. You've already done that. Or you will do that. And it's kind of also in the project, too. So these are very concrete things. You can write them down. Okay. Now, here's the thing. As we've moved from here to here, we've kind of lost some structure. Here I know about every single simplex. Here I also know about every single simplex, their basis vectors. Here I've lost track of some of them. I now only know about, say, connected components. The equivalence class of those vertices that are connected to one another, or the equivalence class of those edges that form circuits, closed loops. And furthermore, I've gone from inclusion, which is a very particular kind of set map. Takes elements to elements, it's injective, it's continuous, all those sorts of things, to just general linear maps. So I've lost a lot of information moving through this.
Is that how we're defining connected components as an equivalence class?
Yeah, you can think of them as an equivalence class. Yeah. I haven't been very precise about that in this course,
Yeah.
because to make it precise requires homotopy theory, which is another kind of algebraic topology that I don't want to go into. Okay, so the point now is, I have a lot of structure here. This is very detailed. And this is This is considerably coarser information. But assuming that I've preserved structure all along, I can tell you exactly what the union of two sets are as a set the moment I know what the intersection is. If that's the case, if that is that much information packed into here, the same kind of thing ought to be happening over here. Especially because we kind of know what's going on over here.
So you're saying that given that we know the bottom element, we're able to go backwards from the union?
Yeah, we should be able to go kind of back, oops, this one is wrong. That should be union. But yes, given the fact that I know A and B, and I know their intersection, I should be able to make some inference about the union.
Meaning that you know the functor of A and B. You know the functor.
Yeah, I know what the functor does to them, yeah.
Right.
Right. I just need to figure out a way to tease it apart out of these linear maps. That's the goal. Okay, so how do we do that? Well, the cleverness of what's called the Mayer-Vietoris exact sequence is to recast this diagram in a slightly different way. This is a vector space, yes. This is a vector space. These are linear maps. All four of those are linear maps. So I could do something to them in a particular fashion to make things a little easier to work with. We're a little different. Because I've got some extra structure going on here, see what's happened is I went from a very detailed description to a description that in principle can hold more information. This is fairly rigid. This is fairly rigid. But in here, this is very flexible. That's the intuition. So I've got something which is very rigid. I'm going to imagine it being part of a very flexible space. And then I'm going to apply some constraints and turn it back into something very rigid.
Sounds a lot like the things that we did at the beginning of the semester.
Yes.
We have these two constraints, and what does this have to be so that X and Y are satisfied?
Yes, exactly. So now, let's make that happen. See, here's exactly what's going on. Let me start labeling these things. Let me call this map I sub A intersect B into A. I sub A intersect B into B. I sub A into A union B. I sub B into A union B. So I've labeled these four maps. When I think about what these four maps are over here, they're injective chain maps. They're linear maps. This vector space and this vector space here, without too much loss of generality, I can do something to that. See, this map here would be I sub, we call it capital I, A intersect B into A, capital A intersect B into B, capital A into A union B. Now, those are linear maps, matrices. They have a certain rank. They have certain kernel, certain co-kernel, certain image. All of the information about linear maps are encoded in those four spaces. Everything there is to know about a linear map is encoded into its rank, so the dimension of its image, and how it fits together with its kernel, how the image and the co-kernel fit together. Let me ask you the following kind of Socratic question. Is the information encapsulated in this diagram changed at all? From a vector space standpoint, they make the following change. If I put that red minus sign in, does that change the vector space content? No longer corresponds exactly to this kind of map anymore because I got minus signs floating around, but it changes the vector space content.
Does that mean add a minus sign to
Well, I'm just saying, take that matrix and every entry, just flip the sign on it. It's a matrix, flip every sign.
No, I don't think so.
No, it doesn't change the vector space content at all. That's part of the flexibility. Like I could change bases as well. That too wouldn't change the vector space content. That's what I mean by flexibility. Here you have choice of bases.
Well, wouldn't the diagram fail to commute in that case?
Something very cool happens.
Uh-oh.
And this was the observation that makes the Mayer-Vietoris sequence work. What happens if I take an element here and pass it through this side? Let's say I've got a vector v. It's now a vector v just in a bigger space, so there's a vector v over here. What happens if there's a vector v over here? Fine. Now it comes out minus. It's exactly opposite sign than the one that I had over there. You're right, this is no longer a commutative diagram. But that commutative diagram, this means that I can do the following. I can take these two vector spaces and smash them together. And here's the observation. In fact, let me be very specific about it. Let me pick CK. I'm going to take my two spaces that I have here. I'm going to just smash them together, concatenate their bases. Now, going from here to here, I've got a matrix, block matrix, with one column and two block rows. The top block column is this matrix. The bottom block is the other matrix. I want to fill in the narrow here as well. Well, this is now a block matrix, but now it is a 1 by 2 block matrix. On the left is whatever was going on with A, and on the right is whatever is going on with B. Now, the original diagram, the one that didn't have the red minus sign in there, was commutative. This diagram is not commutative, but this diagram has something very, very special. What kind of diagram is this? Well, what happens if I take an element here, a V, map it through this matrix, I get a VV basically. Map it through this matrix, I get a V minus V. I get 0. What kind of diagram have I made? I made a chain complex. So by doing this throwing this minus sign in there and then smashing these two spaces together, I made myself a chain complex, where I didn't have one before. Even better than chain complex, this is like the union of A and B, which means that the union of A and B is determined exactly by A and B. So the only things that really got set to 0 over here are the things that started out matching over here. Surprising, surprising theorem. This is an exact sequence. If I call this guy script I, and call this guy delta, kernel of delta is precisely the image of script I. Now, both of these were injective linear maps. They remain so. So, exactness playing along here, this is a way that I can encode the fact that I is injective. Because this is saying that the kernel of I is the image of this map. The image of that map is 0. Similarly, assuming that A and B cover A union B, which surely they do, this is surjective. Voila. Very nice. Now, this is true for every single K. So I get one of these exact sequences for every single K. So by making use of the flexibility that I have at this stage to drop in an extra minus, basically do a sort of partial basis change, I'm able to pull an exact sequence out that encodes the fact that the union is determined by its parts and something about its intersection. This is pretty super powerful, and it gets more powerful. Now, I'm not going to tell the full story now, because I'm saving part of that for one of the presentations that we'll hear about. Because I get a whole bunch of these sequences, one for each K. So I can stack them.
And then we build chain maps.
And then you build a big honking threaded exact sequence through this whole mess. A big honking threaded chain map. Well, not even chain map through this whole thing, it's an exact sequence. This, in fact, is generally called a short exact sequence because it's not very long. It's only, well, really it's basically just one interesting step and 2 easier steps. Starting out with that long exact sequence, or starting out with that short exact sequence, I get a long exact sequence. It's a theorem, although for whatever reason it picked up the name lemma. The snake lemma says if is a collection of exact sequences amongst chain complexes then the following sequence is also and it goes something like this. Starts out pretty reasonable. And then it does something amazing. Does something amazing. Is that it repeats. And of course over here it also repeats. Yep, dropping down in dimension each time you go. Yep, as you follow the boundary maps of each of your chain complexes. The proof of this is a lot of fun. It's one of our presentations. Really the key points are these maps here. These go under the name of the connecting homomorphism. And they do something pretty handy. They link up one homology degree with the next. Robert Grice, the author of one of our books, says that any person who wishes to call himself a topologist should be able to, at the drop of a hat, compute these for you and explain them. So we'll see. Now, what does that do here? That connecting homomorphism does something really very handy here. What does it do? Well, let's take this and transfer it into that format there. You transfer these symbols into that particular diagram there. In particular, let's look at it just at dimension 0, just to get a handle on what's going on. So I'll start out. Let's see, where's my A, my B, and my C? What are my A, my B, and my C? Actually, I'm going to make use of the fact that I've got a whiteboard. This map continues. And it ends because after a while everything else is 0. All right. So what are my A, B, and C? In this, I'm just transferring this over to here. A is the intersection. So everywhere I see an A, I'm going to replace it with the intersection. Everywhere where I see the B, what's that? Yeah, so that's going to look like this. Homology has a nice functorial property with regards to sums. And C is the union. Okay, and of course this thing goes on up the chain too. All right, now, how does this allow me to figure out what's going on? I want to find the unions. I want to understand how the unions are constrained. This is our goal. Those are our goals. What do we know? We know basically what's going on the other side of things. So in particular, I know this is an exact sequence. If I know something about A, and I know something about B, and I know something about how they're fit together, what does this do for me? Well, it's an exact sequence, right? So I know that this map here is what? What do I know? No, it's not 0. This is an exact sequence. So what is this? What about this map?
Full rank?
It's full rank. It's a surjection. I know this map is a surjection. Now, what here got stuck together? Well, whatever got mapped through this map here. So if I know something about how the intersection fits together, in fact, I know everything about what's going on here. If you look at this here, what is this really telling me? This is telling me something about, take the set here of, let's say for a moment, I'm going to pull the inclusion-exclusion principle out of this. What happens if my A's and B's, these complexes, are just points? What happens if they're just points? They're just vertices, no higher dimensional bases. Well, what does that tell me about H1 and so on? All 0. Right. So, easy case. A, B are just points. Then, each k of A, of B, of all the homologies in dimensions 1 higher go away. So then our exact sequence is 0 maps into H0, A intersect B, maps into. Okay, this short exact sequence. And what does it the dimension of H0? It is the what? Well, I've got just points here, right? Just have points floating around. And so, let's see, H0 is the kernel of boundary 0, which is all the points, modulo the image of boundary 1, but there are no edges, the image of boundary 1 is 0. So each of these are spaces whose dimension is the number of points in each of their respective sets. So this is 0 maps are number of points in A intersect B. R, number of points in A, direct sum, R, number of points in B, number of points in A and B. How do I know? Well, I know that this map is surjective. So this applies a bound on the number of points in A union B. In fact, this is an exact sequence, right? So the kernel of this map is precisely the image of this map. This map here, however, is injective. So that means kernel of this map, the dimension, let's see, what is the dimension of this? This is saying that the kernel of this map, being that dimension of this space, the entire space here, well, gosh, what does that tell me about the number of points? Oh, that says, this means that the number of points in A union B, it's exactly however many points are in here. That's how many points are in here, minus. And that, of course, is the inclusion-exclusion principle for points. So what do we gain by doing this? I mean, because this would be a rather silly result to be doing all this machinery for. Yeah?
Well, but not only do you have that, you also have a snake lemma.
Well, okay, fine. No, the point of the matter is not so much that I have the snake lemma, it's that I have this long exact sequence. It generalizes up. What I've done is I've shown you that this Mayer-Vietoris exact sequence, this big long exact sequence, is a strict generalization of this. The exact sequence is a strict generalization of inclusion-exclusion. But better yet, since it ended off at 0, I could do an induction and build up everything else. Inductively compute and relationships. They're relationships encoded as the linear maps in this exact sequence. So what that means then is that really means I can tell something definite about all the homologies of the bigger sets from the smaller ones. So now the big zigzag diagram, that means that anything above that second level I can compute in terms of all the lower levels. Now, maybe a little bit involved, but nevertheless, it's possible to be done. And that's the point. The point now is if I go ahead and compute from each of the various bits, the samples that I can manipulate, I can compute homologies for them, and then use this exact sequence to sew them together. Yeah?
So when you're, so let's say that we're playing with actual data, and you're starting out with the, like a diameter for the Mayer-Vietoris strips, what diameter would you choose?
Ah, right. So what I haven't said is I haven't talked much about the persistence end of this. The persistent homology also is a functor and allows you to drag all of this for the ride. And actually, the paper that I pointed out touches on this and basically assumes this is background. says this is the sort of standard thing. The algorithm that they built out shows how to extend this into persistent homology. Grab all of that generality and make use of it. And additionally, actually they provide a computational algorithm that actually terminates for computing these sorts of things. And that's a great place to stop. So we'll pick up next time. Okay.